Most people solve this problem in O and O of n squared, and LeetCode absolutely destroys their solution.
Hi everyone, and welcome back. Imagine having 3 possible jumps from every index of an array. You can jump to the left, or to the right, or to any index with the same value. Sounds hard, right? But today I'll show you how to solve the LeetCode problem jump game number 4 in a linear time using one powerful technique, which is breadth first search. And also, there is one tiny optimization that it changes the solution from almost quadratic to linear. Today, we are solving one of the most interesting breadth first problems in LeetCode, which is jump game number 4. These problems looks like a graph problem hidden inside an array question. And the key to solving it efficiently is recognizing that every index is actually a graph node. So we are given an integer array, and from any index I, we can jump either to that index plus 1, or from that index minus 1, or to any index that have the same exact value. And our goal is to reach the last index using the minimum number of steps. And as a rule of thumb, whenever you hear minimum operations or minimum jumps, you should immediately start thinking about breadth first search. Why? Because breadth first search explore level by level, and each breadth first level represents one jump. So the first time we reach the last index, that automatically gives us the shortest path. Now, let's transform this problem into a graph. So each index in the array will becomes a node. And from index, for example, I, we can go to I plus 1 or I minus 1 or every index with the same value. The tricky part is efficiently finding all the indices with the same value, because moving one step forward or one step backward is straightforward. So this is the tricky part, is finding all the indices that have the same exact value. And to do so, we will use a hash map, where the key is the number and the value is the list of all the indices containing that number. So let's take an example. Imagine that we have an array that looks like, let's say, 3, 4, 2, 3, 3, 2. So we will build our hash map so it looks like when the number is key, that maps to the list of 0 and 3 and 4. And for number 4, that maps to the list of only a single element at index 1, and the last element 2, and that maps to the index 2 and 5. Now, from any index, we can instantly find all the same value position. So now let's go to the code and try to understand the solution step by step. As we are using a breadth first search, we will need two things, or we will need three things. First, we will need a queue. Second, we will need a visited array. And third, we will need a step counter to count how many steps so far as we are processing the element in the queue. So let's start implementing. First, I'll define a variable called n that will hold the size of the array. And then we will do a quick check that we make sure that our array is not just a single element. So if n equals 1, this is a single element array. In this case, we will return 0 immediately. After that, I'll define my hash map as an integer and vector of n. So the key is integer and the value is list of integers. And let's name it, for example, same value. And after that, I'll iterate over the elements of the array and I'll push the key at the array of I. So the key is the number, and I'll push each index that have the same number. So till these steps, we created something like this map in the example we have seen before. After that, we will define the queue for our first search, queue of integer. Let's name it queue. And we are starting at the first position of the array. So we will push the first element, or the first index, in this case, to our queue. And also, as I said, we need another thing for our first search, which is the visited array. So let's define vector of Boolean. Let's name it visited of size n, and I'll give it the value false or initialized all the values to false. And also we will set the first element to true because we are already started at the first element. And don't forget to define the variable steps that will hold the final answer after processing our queue. After that, we will continue normally with the press first algorithm. So first we will check that our queue is not empty. So if it is not empty, remember that we need to process our elements level by level. That means that if I'm an index 0, then I can move to index, let's start with another index. If I'm at index 3, for example, I need to explore the index at 4 and the index at 2 and all the indices with the same value. See, so let's name this is a level. So we need to check that level first before moving to the next level. So to do that, in first search, we need to define size, which equals the size of the queue. So we can process all the elements currently associated with that level before moving to the next level. So this is processing level. By level. And after that, we will get the front element of the queue. And don't forget to pop it from the queue. so not to process it again. And after we getting the index, we need to check that if we have already reached the last index of the array. So if index equal in -1, then we will return the steps variable. After that, we need to explore our valid movement. So first we can move to the left. So I need to check if our index -1 is greater than or equal to 0, and it is not visited yet. So visited of index -1. So in this case, that means this element is not visited and it is within the boundaries of the array. So I'll set the visited to true to mark it as visited. And I'll push this element or this index to our queue. And similarly, we will do the same for moving to the right. But at this time, we will check that index +1 is less than n, and again index +1 is not visited, and if so, we will set the index +1 visited item to true and push that index to the queue. And the last thing is to check the same value jobs. And that we need to iterate over our same value hash map for that index. So for int, let's name it next index in same value hash map for array of index. So here we get the list of indices that have the same value. So for example, if our value is 3 in this example, then we will return this list here and we will iterate over each index in it. And again, we'll check if that next index is visited or not. So if not visited of the next index, then we will mark that index as visited. It's almost the same as previous, and we will push it to the queue. And here it comes an important optimization, which is this optimization is very important for the entire problem, which is after processing all the indices with the same value, we need to clear the vector at the same value. We need to clear the associated vector in our hash map. So we need to write here that same value of array index dot clear. And this is absolutely critical. Why? Because imagine that we have an array that is filled with thousands of identical numbers, and without clearing this list, Each time we process the same number for the second time or the third time, we are looping through the entire group again and again and again. And this is create a massive of repeated work. And by clearing it after the first use, each same value group is processed only once, and that reduced the complexity from nearly n squared to down to linear time complexity. And finally here, after processing the level, so from this while loop, we need to increment our steps by one. And if we didn't return after while processing the elements in the cube, that means that we can't reach the last element, and here we need to return -1. So let's run it to make sure that we don't have any syntax error. Actually, we have which one? Steps is misspelled. Steps here. Yeah. Steps. Okay, let's run it. And again, aha. Oh, my bad. Here we go. Let's submit it. And as you can see, in terms of time complexity, building the hash map takes O of n, because we are iterating over all the elements in the array. And the breadth first solution also overall takes O of n, because each index is processed only or visited only once, and each group is processed only once. So the total time complexity here is O of n. For the space complexity, it's O of n, which is very optimal for this problem. And that is the optimized breadth first solution for the jump game 4. This problem is a great example of graph modeling, breadth first search shortest path, and eliminating repeated work using smart optimization. If this explanation helped you, don't forget to like the video and subscribe to the channel. And thanks for watching. I'll see you in next one. Bye.